All right, thanks for having me at this very exciting gathering. So yes, I am Rito. I am from Caltech JPL. And I'll be telling you about the earliest achievable glimpses of our own universe and how we can learn about fundamental physics by looking at things such as the CMB. So you already saw this beautiful timeline of the universe in Suzanne's talk, and how the CMB at the recombination epoch right there enlightens us about the universe at large. My talk will focus at the very earliest bits of it. How can we use the CMB, for example, to talk about this sort of hidden sector, if you will, in timeline? So brief reminder for those who just came back. The CMB is a shell of light that we see around us. It comes from a particular epoch in the early universe, prior to which the universe is very hot, and it's ionized plasma, and light is constantly scattering. It doesn't travel freely. But then, as the universe is expanding, it's cooling down, and there is a particular moment in time everywhere in space you get the formation of stable neutral atoms like hydrogen and helium, after which light travels freely. The universe is transparent. And we see, therefore, this shell from where we are, smiley, happy face. Now, the shell is a brightness, right? It's a brightness of this light. And there's a texture, these anisotropies that Suzanne talked about. And that texture tells us a lot about the contents of the early universe, its geometry, the timeline, and all of that good stuff. There's also a lot of correlation study you can do by asking, is the texture around this area correlated with that area, and so on. And when we do that, we see that there are regions of space that should not be connected. They're farther apart than light travel distance that are quite correlated. And to explain that, we have this theory of inflation, which you again heard from Phil and Suzanne. So how do we use the CMB to detect the earliest signatures of the universe right after the Big Bang, this process of inflation? So as a reminder again, inflation is this process in which we believe the universe expanded immensely, 10 to the power 60 times. That's a pretty nutty number to think about. But it also did this in a very tiny amount of time, at 10 to the minus 32 seconds, a time scale we don't quite deal with on earthly experiments. And this violent process, if you will, shutters space-time, and you have these primordial gravitational waves that travel through. And you heard about this in the nanograph talk, of course, from Mara. Now, in the CMB, the way we can see this is as the gravitational waves are propagating through cosmic time, when the CMB photons come out, the gravitational waves put an imprint, a fingerprint on the CMB. Particularly, they introduce these curly, swirly patterns you see here. And if we can detect these so-called B modes, you can actually talk about the early universe physics, and these are energy scales that are 10 trillion times larger than what particle colliders can achieve on Earth, and that's the exciting part. So here's just glamour shots of our work with the Keck telescope at South Pole, Antarctica, where we run these cryogenic devices. You can see the cryogenic camera here at the belly of the telescope, these big tubes, and they then sit in these sort of buckets or ground shields operating at South Pole. And it's a thrilling experience to work in Antarctica, this crazy environment. And I kind of wrote up my travelogue, if you will, and got published in media if you're interested. But the heart of it is that these cryogenic detectors that Susan also alluded to do the measurement of the CMB. So we have these telescopes. We understand what we're looking for. Where are we today? So this is one of the most complicated graphs, I promise, and things will get easier. So this is showing the signal strength, or the amplitude, of these curly patterns, or B modes, as a function of angular separation on the sky. So are things far apart at 1 degree or 90 degrees, and so on. What we expect is this faint signature in the double dashed line you see here, labeled with R. But what we measure is this big red hump here. And this is a gravitational effect as well, but from the local universe. And there's a slew of experiments that are trying to get there. Currently, Keck, my experiment, is pushing the boundaries very hard. And the black markers are our newest results. And we are seeing something. We're not quite sure there. And we have to go a little deeper into the foregrounds and all of that. And we're, of course, not the only people doing this. There are other experiments, such as Simon's Observatory, South Pole Telescope. And together, we hope to dig down and detect the signals from inflation. And that's sort of how CMB informs you of the very earliest stages. So now comes the part where I get provocative, as James requested. So think of this as bookends. We talked about T0, if you will, inflation. You heard all about the CMB and everything after that. What about this stuff here, the middle ground? So this is originally, was thought of as a difficult problem because, again, it's ionized plasma. You can't see through it. You cannot see through fire. And so it's sort of this opaque body. And so I, started thinking, can we break through this wall? And can we see this? And why do you want to do that? Not just to, push around things, but because there is interesting physics. This is at an energy scale that is very high, and we don't have access to on Earth. And there are interactions happening in this early universe, as you heard. The energy density of dark matter is very high at the early time scales, where you can expect the energetics to put some signature in the CMB that comes after. So that's sort of the setup. So let's see what the next slide is. Yes. So this is a picture I took on a drive here. So here's a nice picture of nature, black and white. You can identify water, rocks, vegetation, fine. And that's all you can do, really. You can talk about the waves, perhaps. But once I add color, you can do a lot more, right? You can look at the water's clarity, talk about algae contamination, whatever. You can look at the pigments in the flowers, admire their beauty. You can look at the rocks and tell me what's sandstone, what's quartz. And so the punchline here is that textures and images tell us about morphology, but spectra, or the color, tells us about the internal workings, the atomic transitions that we want to pursue, the quantum transitions. And that's where the color comes into play. So the CMB's color has been measured, as was mentioned, by the COBE FIRAS satellite, and it's a black body. It's a very nice, smooth black body. However, if you do the calculations a little more accurately, you quickly realize it should not be a perfect black body. There should be deviations. Add to that the fact all this exotic physics at higher energies, such as dark matter decays and whatnot, should also add to this distortion from the black body. And why is this relevant? So now I'm going to put my particle physicist hat on and talk about the standard model in one little graphic. So if you look at all the particles that we know of, the photon, i.e. light, the way you're seeing me, is connected by first degree or second degree to everyone. So it is not surprising that all sorts of interactions will live and imprint with the photons. And there's a cartoon just showing what kind of spectral distortions you may have. You can have energy addition and subtraction, for example. And this is, again, expected from standard model, but also from new physics that we want to get to. And to do this, we need new measurements, new accurate measurements, parts per billion, not easy to do. Or else, the great team of FIRAS would have done it. OK, so in this adventure, I came across some colleagues at Caltech JPL who are astronomers on the first end. And they were saying that, hey, between you and the CMB, you have to deal with the whole universe. So you cannot just keep talking about early universe physics and cosmology. You have to deal with everything else. And as it turns out, if you take a holistic view, there's a lot more to get for your instrument time than what we normally do. Particularly, the earliest atoms that formed are molecules, the ionized carbon, nitrogen, oxygen. They will emit. They will have their own quantum transitions that will send out photons that will enter your telescope. And if you look at the spectrum, this is just color and intensity. This is the mu and the y here are the CMB spectral distortions I'll get to, but all this other stuff is atomic physics that will teach you about the universe that's in between, star formation, large-scale structures. There's a lot to learn. So if you can measure this kind of spectral distortions of the CMB, you get a lot of bang for your buck. Now, particularly going back to the early universe physics, this mu distortion, the yellow ochre color, that can encode many things from annihilating signals of dark matter to all the way inflation again. So as inflation happens, there's all this energy density that is being dumped into the universe, and that is encoded somewhere else as well. And it's encoded in a color change of the CMB, a very small amount, but it is there. And so how do you do that? You need to build something that can not only, like the camera, the picture I talked about, that takes an image but also gives you color depth, that also allows you to simultaneously say, I see a dot, that dot is red. I see a dot, that dot is blue, like so. And the motivation here is to create something called a hyperspectral imager. It's in the name, what it means. And the way I think about this is, can we sort of ride on the success of standard CMB experiments but do something novel? So, whoops. So this is, again, the focal plane, the cryogenic focal plane of BICEP array. If you take a magnifying glass and look in, you will have thousands of these antenna-coupled detectors. These antennas collect the photons, and they sum the power, and that power is measured by these detectors. What if we intercept that signal with a broadband spectrometer that is very compact, because I cannot increase the size of this focal plane. This is already hard to build, and has enough color resolution that I get my physics out. If I can do that, then I'll have thousands of eyes on the sky simultaneously, and you get some picture like this. You have the galaxy, but you see it in color as well. So that's a challenge. It's not easy to do that. Again, if it were, people would have done it. We started an R&D project, particularly Phil's group and my group, where we wanted to build something like a LIGO on a chip. Sounds quite ambitious, and it is. So you heard about LIGO as the interferometer. It is analogous. It is not measuring gravitational waves. We're dealing with photons, light. And this thing you're seeing is a Fourier transform spectrometer. It's operating at about 20 to 40 gigahertz. If you wanted to build this in the lab, and some of us, I'm sure, have done this, it would be 2 meters, 6 feet in size. But this guy is only 6 millimeters. It's very small. And as a prop, I have one in my pocket. I can share this around. So we did first fabrication and testing, and we get what an interferometer should do. We get a cosine or sinusoidal modulation, and now we are kind of improving that technology and seeing, can we realize these thousands of eyes on the sky that can take color pictures? So this is perhaps gratuitous, but I will compare it with old computing and new computing. So the Harvard Mark I von Neumann used is an electromechanical computer. The state of the art so far are these optomechanical Fourier transform spectrometers. And inspired by what happened in the silicon industry, we are trying to go in the superconductor industry and make photonic circuits on chip that can do all of this at millimeter scale, so you can have high throughput, high efficiency. So plans are, of course, to build an array of these and look at the CMB and take a color picture of the CMB and see if we see these spectral distortions and extract some deep physics from them. We're also exploring use in quantum optics. There's a beautiful testbed for doing correlation studies, probes for dark matter and astrophysics with this kind of a new device. And I'll back up now as to the utility of this device in the context of the CMB. So as I mentioned, there are all these spectral distortions, including the first hydrogen and helium transitions in the universe that you could see if you could measure the CMB spectrum very accurately, because the CMB came from them. And I wrote a white paper with a bunch of colleagues in Europe that has a full storyline of the discovery space that this kind of singular measurement can get you. Before our on-chip interferometer came to life, European Space Agency said this is a thing they want to pursue for the 2050 voyage. And now I have demonstrated a technology, I hope, that can get there faster, better, and cheaper. And with that, I will go to the conclusion. So we have two ways to look at the early universe using the CMB. One is the texture in the polarized images that tell you about these B modes from inflation. The other is to talk about the color. Oops, something happened. Huh? Oh, OK. Well, anyway, I can yap. So one is this picture, and the other is color. And if you have this color granularity, you can learn about energy injection processes that tell you a lot about particle physics in the early universe. And in the pathway, we came up with this new technology that is turning out to be useful for other fields. So we can cross-pollinate and try different experiments with it. And that is the end of my talk. And I'll put the thank you slides and say that BICEP is a big collaboration. We're supported by NASA and SF. And the SOFTS thing is a new collaboration. We just started a year ago, and it's growing quite fast. And these are all the people behind the scenes who make this happen. And thank you for your time.